Okay, so in this video, I'm gonna be proving the general chain rule for multivariable functions. So this is just gonna be concerned with functions that are both vector valued. So I've seen a lot of videos where they're proving the chain rule where there's still a composition. So what I mean by that is um, something like this. So they would have, let's say, G, small g, mapping from R n until R. So basically a scalar valued function. And then they would have some f. So, and then this would be mapping from R to Rn. And then this would be a vector valued function. And then they would take the composition. So basically this would look like f of 1x having f1 up to fn. And this would basically look like g of x1, maybe x2, all the way up to xn. But then this would only have one output, g, hence scalar. So then they would take the composition. So, and they would find the chain rule. Now, this proof is going to be very different from this, because what we're going to be doing now is we're going to be considering compositions that are both vector valued. So in order to do that, we're basically going to take the same idea from this proof. So the way this one would be done in terms of its formula. So we know that its formula can basically be broken down as follows. So if you want to take the chain rule of this scalar scalar composition, you're basically just going to take the derivative of the whole thing and then just the derivative of g, just like that. And then this can be extended to taking the gradient of f at, sorry about that, be the gradient at g of x dotted with the gradient of x. And then this can further be extended as to taking the product from I equals to 1 up until n of the partial derivative of f with respect to g times by the derivative of g with respect to t. So here, with respect to x, sorry, x, and this basically comes from the idea of having that middleman as we are trying to get to a certain derivative, a certain derivative using the chain rule. So I won't go into much detail about this, but it's basically the same concept. So what we have to do is, so the first part of this proof would be taking the summation of such a composition. So the derivative would basically be like taking, okay, so before we go there, the thing you have to notice is that in a case like this, what I did was I listed the function representations as this, and I find it very useful to have the same approach here. So firstly, g is going to take in n inputs. So let's say from x1, maybe x2, up until xn. And what is that going to give out? That's going to give out P outputs. So it's just gonna look like, let's say, from G1 up until GP, just like that. And these, very important to notice the distinction between this. G is taking in N inputs and spitting out P outputs. And the same idea goes for F. F is going to be taking in P inputs. And now this is important. Notice the relationship here. F is taking in P inputs and G is going to take out P outputs. That's a perfect relationship for a composition. So from x1, maybe x2 up until xp, and then splitting out M outputs. So basically something like F1 all the way up to Fm. So before we enter the proof also, the whole idea of the chain rule is that we're taking the derivative of some composition. So if we're taking the composition, well, this can be represented in many ways. For example, it can be written as F small circle G, something like that, or basically F big F with the composition of G. So basically it's much easier to look at it from this point of view, but they're both equivalent forms. So now what I want you to notice is how this is going to change. Notice F is taking in P inputs. G is giving out P outputs. That gives us a perfect opportunity to align our outputs of this function, to align our inputs of this function with the outputs of this function. And what I mean by that is it's going to change from mapping from Pn to Pm. Sorry about that. F is going to change its mapping from Rp to Rm, simply because now we're taking the composition. And the fact that, like, you have to link these things. G is giving out P outputs, but has taken in N inputs. That means that the composition is going to map from Rn to Rm. Because what you have to understand is that F composition G is completely different function from F or G respectively and individually. Hence, we have a change of, basically a change of domain and codomain in terms of weight maps to weight maps. So as long as you understand this, the idea of derivatives in general in multivariable functions should be quite easy to understand as well. Because also taking the derivative of something like this, you would obviously know that that derivative matrix would be M by N matrix, and that is extremely important in this proof. Okay, so the first thing we would need to do is now get that summation. So let's see how this is going to work. We're going to take the sum from, okay, let's see, it has to be from, so we need to end our summation at the number of inputs of F. So this is going to be from M equals to 0, from M equals to 1. From M equals to 1 until P. The reason behind that is similar to how it was when we took the composition of a scalar valued function. It's because we have to take the derivative with respect to x1, x2, all the way up to x. Yeah, we have m functions here. So in order to take its derivative, we need to take the derivative m times, because we're having basically m outputs. So the outputs would be, for example, here, the partial derivative of f1 with respect to x1, the partial derivative of f1 with respect to x2, the partial derivative of f1 with respect to x3, and so on, all the way up to the partial derivative of f1 up until the partial derivative of f1 with respect to xp. So that's why we need to start from m equals to 1 up until xp. So I hope that makes sense. Again, we need to take the partial derivative of f. F is our main thing in this proof. So it's going to be f m up until xp. So that's what I just said right now. We're taking the partial derivative of f1 up until xp, then the partial derivative of x2 until xp, and so on. Now, because this is vector valued functions, we have to keep in mind that you can't take a partial derivative of a single variable function. Hence, that's the only reason why we're having partial derivatives here. So continuing, we would take the partial derivative of g. Now the same idea goes for here. We're going to be taking the partial derivative of g1 with respect to x1, partial derivative of g1 all the way up to xn. So we're going to be going for all our equations or outputs of g, so up to partial derivative of gp with respect to xn. Now there are certain function evaluations at this, but we'll put that in last. But I do hope that you understand this. Here we're taking the partial derivative with respect to f1 of f1 with respect to x1 up until fm with respect to x1. Then we're going to f2, taking the partial derivative with respect to x1 up to xp. Okay. Now that we have this, what we can do is get these are basically like what they can form are row and column matrices, and we know those just to be for example, a row matrix would just be a matrix having one row and any number of columns, and the same can go for column matrix. So we have to, as you can see, a product is being taken here, so it's a sum of these products. So what needs to happen here is we have to take the matrix, row and column matrix, and an important thing to note is matrices have certain conditions for its multiplication, and that condition is that the number of rows in the first matrix must equal to the number of columns in the second matrix. So that's what we're going to do. We're already given that this is a row matrix and a column matrix, so it's going to be equal. So how is that going to be? It's exactly what I said here, and it's exactly the application of this. So for f, it's going to be partial derivative of f1 with respect to x1 all the way up to partial derivative of f m with respect to xp multiplied by the column matrix containing entries partial derivative of g1 with respect to x1 all the way up to the partial derivative of gp partial derivative x n. Okay, so now that we have that, we can now write this from the definition. We can give the composition. So the third part would be, this is now where we're gonna be utilizing this idea. Very important. So if you're taking the derivative of this composition, okay, when you're taking the derivative matrix, those are going to separate. Well, not separate, they're just going to swap. So our derivative matrix is going to be m by n. So something like f g, so f1 x up until f m composition g x. And this is just going to be equal to, remember, this has to be a m by n matrix. So it's going to go from the partial derivative of x1 f1 composition g with respect to x1 all the way up to the partial derivative of fm composition g with respect to xm in terms of its rows up until partial derivative of fn composition g over partial x1, and then partial fm composition g with respect to xn. So we have n columns, so this has to be n we have n columns and m rows, so this has to be with respect to xm. I hope you see the idea that's going on here. Now that we have this, we can finally do our conclusion. That would be part 4 would be just breaking this up into what we know it to be, into its constituents. Initially the problem was viewed as f maps from rp to rm, so that's the same idea that's going to carry us through here. It's going to be but now that we have the derivatives, we have to swap them as well. So it's going to be the partial derivative of f1 with respect to x1. So it's going to be m rows, p columns. M rows, p columns. So up until f, partial derivative of f m with respect to x1 up until the partial derivative of f p with respect to x1. So we said there should be m rows and p columns. So partial derivative of f1 with respect to xp. I hope that makes sense because it's really sinking in for me. Partial derivative of f n m with respect to xp. This is where we can do our function evaluations. This is going to be evaluated at x equals g of t dotted, think dotted. And then the same idea goes for g. G was being mapped from Rn to Rp. So this is just going to be a matrix with p rows and n columns. So partial derivative of g1 with respect to x1, partial derivative of g, so we said they are going to be p rows, partial derivative of g1 with respect to x p, all the way up to partial derivative of g n with respect to x. Okay, so we said it has to have p columns and n rows. So partial derivative with respect to x n or g1. The same is going to go for the last entry. Partial derivative of g so there has to be p rows and n columns. So I think I see an inconsistency here. No, there's no inconsistency. We're taking the partial derivatives row by row. So the first row is going to have the first set. So what I mean by that is, can you see that its output, for example, here is G1. G1 is going to definitely contain variables x1, x2 up to xn. So this row is basically taking the partial derivative of G1 with respect to all of those. So it's going to be the same idea here. This is going to be so we have p outputs. So the partial derivative of g with respect to p, the partial derivative of gp with respect to x1 up until the partial derivative of gp with respect to x. So this has to be with respect to p as well. So with respect to p. Because remember, here we're taking f mapping from rp to rm, and here we're taking from rn to p. So this has to swap, having m rows and p columns. And the same idea is here. And then we can finally conclude this by saying that the chain rule for multivariable functions is given by f prime g of t dotted with g prime of, sorry, this should be x. X, done. Okay, so that's the proof. Okay, thanks.